Okay, time to start. Welcome to lecture 9, CMOS. So we're going to go kind of back to the bottom and start at the bottom, which means we're going to talk a little bit about IC processing. If you haven't seen this before, you might learn something. It's just kind of a brief overview on the processing needed to build chips. And we'll talk about how we model MOS transistors. This isn't a physics course, so we're really not going to talk much about the physics, but we'll talk about the models that are important for us to understand, and then how we use the transistors to make circuits. So we'll talk about basic CMOS circuits. Today, if we get to it, it might be probably Thursday, actually, before we get much into circuits. But we'll talk primarily this week about the functionality of the circuits. And then next week, we'll talk about the timing associated with the circuits. And then after the midterm, we'll talk about the power consumption of the circuits. So let's go kind of back to the beginning. And here's an overview of when we implement our designs as physical systems. This is the stuff that we use to make these systems. We have integrated circuits, which we'll talk a lot about today. We have printed circuit boards, and that's the substrate that we put the circuits on. We have power supplies, of course, that provide the power. That could be battery, or it could be something that converts line voltage into what's needed for running the circuits that are on the chips that are on the printed circuit boards. And then there's some way to house all this. If it's a server, then it's in some kind of chassis. The chassis goes in some kind of rack. If it's a handheld device or a portable device, then the chassis is the enclosure for the inside is printed circuit boards. There's connectors and cables, and there's peripherals and I/O devices. The peripherals are things like keyboards and display devices and disks and network connections and that sort of thing. This class, we're really focused primarily on the design associated with what's inside the integrated circuits. So here's another picture. This shows printed circuit boards. These are made out of fiberglass or ceramic. They have about 1 to 25 conductive layers. 8 or 12 is a popular number. They come in varying sizes. They can be made up to about 20 inches on a side. After that, they're difficult to make. And then the integrated circuits are in packages that are soldered down. Right? There's another kind of thing is a multi-chip module. This is where we put multiple chips together on one small module, which could be silicon substrate or ceramic substrate. Sometimes those modules then are soldered down on their printed circuit board. Sometimes these are just standalone and connected to the peripheral devices directly. Okay. So the integrated circuits that we build, they're primarily crystalline silicon, as we will discuss. They range from about 1 millimeter on a side to about 25 millimeters on the side. It's hard to make chips that are much bigger than that. Part of the reason is if we make them bigger, then the yield goes down and they get too expensive to manufacture. The other reason is that the machines that we use for making wafers sort of limit the size of the chip. Okay? These days, we're in the range of, well, a very small chip might only have tens of transistors, but large chips have billions, up to 20 billion transistors these days, okay? And which is equivalent to about 25 to about 250 million logic gates. The conductive layers, the layers used for making connections between the transistors, depends. But we can get anywhere between 3 and 10 or more conductive layers. The state-of-the-art feature size, as we've discussed, is 7 nanometer. So that's 0.007 times 10 to the minus 6, or 0.007 micrometers. And the type of process, the type of chips that we build primarily these days are silicon, on silicon devices is CMOS. which is CMOS stands for complementary metal oxide semiconductor. Good. There's other types of processing out there that are used for special purposes, like really high-speed circuits or for analog circuits sometimes. But most of the integrated circuits in the world are CMOS. In particular, most of the digital ICs are CMOS. Okay, so this is my rendition of a chip that's sitting inside a package, and it has these little wires that make connections from the chip to the package, and then the package spreads those wires out and has these pins along here that are used for making connection to the printed circuit board. And so the package is a thing that sits between the IC and the PCB. And we saw this before when we looked at FPGAs. This is important for physically spreading the signals out and for dissipating the heat. Right? These are typically made out of ceramic. If it's under about 5 watts of power dissipation, then we can use plastic. Much more heat, plastic doesn't dissipate it very well. So high power chips are often in a ceramic package. Okay, so that's the basics. So we're going to talk about chip fabrication for a little bit. This is a picture of somebody inside the factory carrying this tray that has these wafers in it, moving them from one processing step to the other processing step. Right? So these wafers have a bunch of chips on them, and the chips get cut up. The die get cut up and put into packages, but they get fabricated all together. Right? These wafers are crystalline silicon. Okay? And the way these crystalline silicon wafers are made is shown here. There's a crucible down here that heats up the silicon material, which is, then there's a seed, and we grow a crystal. It's kind of pulled out of this molten material, making a pure silicon ingot. There's a picture of one here. Right. And these are very pure. They have very few impurities in them, because an impurity in the silicon can lead to a fault in the circuit. So these are then sliced up with a diamond saw, as shown here. They're cut into wafers, right? And those go to the factory for fabrication. In the old days, the wafers were this size, about 100 millimeters. They've been growing over time. These days are up to about 300 millimeters, which is about 12 inches. The reason they grow over time is that the cost is kind of fixed with the time that it's in the factory, and all the steps are about the same, independent of what size the wafer is. So if you use bigger wafers, you can build more chips at once, and that kind of reduces the price per chip. But the machines that handle bigger wafers are different than the ones that handle smaller wafers, so the machines have kind of been getting upgraded over time. Okay, so that gives us the wafers, and then on the surface of the wafers, we build, at each die location, we build a bunch of transistors, because that's all our circuits are in the end, is transistors and wires. Right? So we just need to figure out, the process gives us a way to build transistors and connect them together. We're going to look at 2 different views of transistors. We're not going to get a lot into the physics, but we'll look at the layout like this. And this is a kind of an artistic rendition of the transistor if we look down onto it from the top, looking down onto the wafer. Right? And we see that there's 3 different regions here that we'll discuss: source, drain, and gate region. Right? And these are these regions here, the drain and the source, are implanted into the surface of the wafer. And this gate region is sitting up on top. For that, we use a material called polysilicon, which is not single crystalline silicon. It has multiple crystals in it, so it's naturally not as conductive, but it gets doped, so it's highly conductive, almost like a metal. In cross-section, the transistors end up looking like this. And this is kind of an old story. FinFET has changed this a little bit, and I'll show you a little bit about FinFET. But this is the old so-called planar transistors. And here's the source region here, and here's the drain region. And these are regions that are down into the surface of the silicon. And then there's a gate region that sits up here. Now, the way these things work is that, let me show you on this picture, which is a little easier to see. We've got a drain here. And these are doped, meaning we inject ions into the surface of the silicon to change its electrical properties. So N plus means that this is a material, and this is a region that has a surplus of electrons. Right? The P regions here they have relatively fewer electrons. They have they're richer in holes if it's a P region. And the plus or the minus just means the amount of concentration. Okay. So this is almost a neutral material. It slightly has a surplus of holes, which is the absence of electrons. Okay. So in this configuration here, we have a voltage here, and no voltage on the gate. Right? If we apply a voltage on the gate of this transistor, plus voltage, is shown here. What will it do? It will pull some electrons from the bulk here up under the gate. So this kind of looks like a capacitor. We got a voltage here. This part is typically grounded. Right? So we have like a capacitor here where you have a dielectric and two plates. Okay? Put a positive voltage here. We get track and negative voltage underneath the gate. And what that does is we say it inverts this channel. This region here is the channel. And it effectively changes it from this P to N type, which creates a conductive path between the source and the drain. Right. So the N transistor, or the NFET, NMOS transistor, is turned on at that point because there's a path for the current to flow from this high voltage here to the low voltage here. Okay. And we'll talk later today a little more detail about the nature of that current. But for now, you can just understand that if you put a high voltage on this gate of this NMOS transistor, then it effectively turns it on, and then we can get a current that will flow from here, if this is connected to a positive voltage, down to that lower voltage there. Okay, so that's the basic operation. They're pretty simple devices as far as semiconductor devices are concerned. Now, we're going to talk about, this is all kind of circuit 1986. Things have changed. There's more, I'm going to talk about how we build these devices. Things have changed. Even a planar process has gotten much more complicated over the years, but the way we build the transistors is different now. As you'll see, we build FinFET transistors. But this will give you an idea of how, if you don't know how we build integrated circuits, this gives you an idea about the steps involved. And it's still close enough to what is current today that I think it's worth understanding this. So if we look at it from the top down, so this is the transistor in cross-section. From the top down, if we look at the masks, so the processing that we do is based on photolithography, which means there's a series of masks that are used for exposing the wafer. And we expose light-sensitive materials, and that's what we can use for patterning these little shapes, or the different shapes on the surface of the chip. Okay. So the masks that we use to fabricate this NMOS transistor is, there's a mask. First mask is the N plus diffusion mask. And this is a mask that's used for defining these regions here, right? And from the top view, it would kind of look like this big rectangle here. Okay. Now, you notice there's no diffusion, no N plus material underneath the transistor gate here, but that's because we'll use the gate to block the implantation of the N+. So the gate will kind of block out a region here, and we'll see that later. Okay, so we use this. There's also a polysilicon gate mask, okay? And this is a mask that we'll use for defining the red, the polysilicon region there that forms the gate of the transistor. There's a third mask is these contact, diffusion contact. So these are points that we'll use for making a connection from a wire onto these regions here, which we can use for connecting the transistor to VDD or ground or connecting it to other transistors. Mm-hmm. And then there's metal mask, which is used for defining the placement of the metal, which makes the connection to the source and the drain. Okay, region. These are the layers that we use for N-type transistors. As you know, we also have P-type transistors. I'm not going to show you that, but it's very similar to this one. Yes?
So what is the reason for using polysilicon on top instead of just like a piece of metal?
The original I don't know, but I know that metal was used in the early days, and then they switched to polysilicon. And I used to know why. I think because of the mismatch in the materials, the transistors are more efficient with polysilicon because of the physics and the electrostatics, but it's just a guess. Yeah?
What's the difference between like source and drain? Because I know in real life...
Difference between what?
Like the source and the drain.
Oh, difference between source and the drain. In this picture, they're symmetric. Actually, there's no difference. It's just how you use them. The terminal that has the higher voltage for an N-type transistor is the drain, and the terminal that has the lower voltage is the source. And that sounds backwards, because the current actually flows from the drain to the source, but you know that current direction is backwards from electron flow by convention, because some mistake of history. So.
I know like on the signal diagram, there's like sometimes a diode from like source to drain or drain to source.
A diode? We don't have diodes here, but you'll see many. I'm going to show you later when we start looking at circuits. You'll see I'm going to label all the terminals. As far as the device is symmetric, as I've shown here. In fact, if you change the voltage, if you made this the high voltage and that the low voltage, then the current will flow the other way through the device. So they can actually be used either way. Usually when we lay them out for purposes in the circuits, they're laid out with the source being, we know which is going to be the source and which is going to be the drain. And for NMOS transistors, this type of transistor, almost always the source is connected to the ground, the low voltage, and then the drain voltage is used for connecting to other transistors, as we'll see. But as far as the physics doesn't actually know the difference. It's just which way you bias the voltages makes the definition of which one's source and which one's drain. Okay, so there's design rules that are used for people who design the layout of these circuits to make sure that things are fabricated correctly. For instance, there's a minimal gate length here. Right? If you made it too small and things got a little bit off in the processing, maybe the gate region would just go away. Right? And then there's like an overlap, for instance, poly overhang. This is so that if things get misaligned, that there's not a short circuit between here and here. So these design rules are put in place to guarantee that during the manufacturing process, even if there's some misalignment of these masks, when things get exposed, that the circuits still function correctly. Right? And there's some minimal kind of resolution that can be resolved, and that defines the size of the process. Right? So typically the gate length it's not shown here this way, but we like to make this be as short as possible so the transistors are as fast as possible. And then there's some metal rules about how much, this is a connection from metal down to diffusion, and there's some rule about how much the metal has to overlap that contact, as we will see. Okay. Okay, so how does the fabricator use the mask set to make the IC? Okay, so this is kind of a simplified story, but this is how it goes. So we start with an undoped wafer. Okay. Step one, it's doped to, we need to make it P minus for this particular NMOS transistor, so we dope that. The way it gets doped is it's put into, these days, there's a machine that will blast ions of the proper type into the surface of the silicon, and then it's put into an oven and it's heated, and these ions diffuse through the silicon. Okay, then we can grow an oxide on here, and we're going to use. You'll see what the purpose of the oxide in a minute. And oxide is like rust. It's oxidation process, right? So if you take this wafer, the silicon, and you put it in the presence of oxygen and heat it up, it will grow, a silicon dioxide layer will grow on it. Okay? And we can control how thick it is by the concentration of oxygen in the oven and how long it's in the oven and at what temperature. Okay? So there's a recipe for doing this. The fabricators have figured this out, and they have a particular formula that they use. So they grow an oxide of a particular thickness, and then deposit polysilicon on top. This is typically done, or used to be done, with vapor deposition. There's a cloud of polysilicon, and it gets deposited through a condensation process onto the surface. All right. So we have that layer. And then there's a so-called photoresist material. This gets spun on. So this is a liquid, like a resin material. It gets put on the surface of the wafer, and then it's spun around so it spreads out and very even. Okay? And then that hardens. It dries. Okay. Then we use the mask for the polysilicon here. That's the polysilicon mask is placed in position, and there's a light source which is used to shine light through the holes. In this case, it's a hole. There's a mask that has holes in it where we'd like this polysilicon to be. Okay, where we want it not to be, it blocks the light. All right. And what that does, the light, this is a photoresist which is sensitive to the light. And what it does is, it's a UV light, and it hardens the exposed photoresist, right, in places where it sees the light. Where it doesn't see the light, then it can get washed away with some kind of solvent, right? So it leaves this here. Right. Now, there's an acid, typically hydrofluoric acid is used to etch the poly and the oxide, but not the hardened photoresist. So this was hardened through the UV exposure. Hydrofluoric acid then etches away everything except right under there. Right. Yep. Yes, hydrofluoric acid would eat through metal. Yeah, in fact, it's used later in the process for patterning the metal. Yeah. Okay, so then we have that there, and then we use the hydrofluoric acid. It leaves this. So this is exactly what we want for our polysilicon gate above the transistor. Okay. Now, we can use the diffusion mask to implant N-type ions. Arsenic is one type of material that would be used. Right? So there's a mask and then ion implanter that blasts the ions into the surface, and then we heat it, and they get diffused down into the surface as shown here. Oops. shown here. Okay, so then we have those regions. All right, and the metallization process. Oh, yeah, one point about this way of doing things is this is, you note how the donor ion atoms are blocked by the gate and don't enter the channel here. So if that mask, the diffusion mask, was slightly misaligned relative to the polysilicon mask, it wouldn't matter, right? We could shift this thing over. It would make this drain or source a little bigger or a little smaller, but the channel would still be exactly the way we want it. And that's kind of a critical thing for CMOS, is the self-aligning of the transistor channel, source, drain, and gate. Because this is kind of a critical thing. This is typically one of the smallest dimensions in the whole chip, because we want those transistors to have a really short channel to be strong. Okay, so precise mask alignment's not needed, and it's one of the tricks of scaling CMOS down to smaller and smaller processes. Okay, so then the metallization completes the device. We can grow a thick oxide on top of everything again by putting it into an oven with oxygen. Oxide grows. Oxides are used as insulator. That's one reason why silicon has been very popular for making integrated circuits, because it has a stable oxide. Right? There's other materials like gallium arsenide, for instance. When it oxidizes, the oxide is like a powder. It's not stable, so it's hard to build these kind of 3D structures. It's a nice property about silicon, and one reason why it's so popular. Oxide is hard. Silicon dioxide is like glass, almost, and it's very close to glass. Makes a good oxide. So we grow a thick oxide here. To make connections to the source and drain, then we need to mask away or cut holes in that oxide, and that's done in a very similar process to what I described before, by putting a photoresist material down, exposing that, stripping some of it away, using that as a mask for some material, some acid or something that will eat through the silicon dioxide, make those holes. And then there's some kind of vapor deposition process to get the metal everywhere. We put metal everywhere, including filling up these holes. In the early days of IC processing, they had problems with reliability because the metal wouldn't make it all the way down into the contact cuts. But one of the rules is how wide the contact cuts have to be in order to make sure the metal gets down there. And sometimes they use multiple different metals, some metal for down in here and then a different metal for making the interconnection. Okay, so there's a metal layer all over, and then we use the masks associated with the metal to pattern away what we don't want and leave just the metal where we want. Okay. And then if there were more layers of metal, this process can be repeated. We can grow another oxide on top, put some cuts in it to make vias or connections, and then put more metal on, and then pattern that, and kind of keep that process going. And things get bumpier and bumpier, but we can go for some small number of metal layers that way. If we want to go to a very high number of metal layers, like 10 or so, what they'll do is actually smooth out the whole surface of the wafer in between adding metal layers by polishing it with some mechanically and chemically to get it very smooth, and then grow another oxide and put another layer of metal and then smooth it out. And as long as you keep smoothing it out, you can go to 20 layers of metal if you need it. Okay, so that's the kind of top-down finished view here. This process, this planar process of building CMOS was invented by this Henri from Fairchild in the 50s. Right? And this became kind of the standard way for making integrated circuits, and it still is kind of typical of the way we make them today. Okay, so that gives you kind of a brief idea on how we could manufacture these things. As I said, the kind of key to this is photolithography. There's some kind of light source, UV light these days. It's focused through some lens down onto the surface of the wafer, and there's a mask It's that the light shines through and exposes the surface of the wafer. It's kind of amazing how it works. The wavelength of the light that's used up until even recently is about 193 nanometers, but we're resolving features that are down to like around 10 nanometers or less, right? So they use diffraction gratings and other techniques to get features on the surface of the chip that are actually smaller than the wavelength of light that's being used. So it's pretty tricky. And so that leads to kind of bizarre masks. There's this technique called optical proximity correction, which is used to compensate for image errors due to diffraction effects. To give you an idea of what I mean, if you look at, see that blue L there, that's the desired feature on the surface of the chip. You can imagine this as a piece of wire. In order to get that, because the interaction between the light and the masks, you have to make a very strange shaped mask. Okay? So there's computer programs that do inverse optics to kind of figure out what the mask shape needs to be in order to get this exposure on the surface. And what you actually get is kind of more roundy thing. So if you look at photographs of chips, things that we draw and think of as really square, ideal shapes end up being kind of blobby things, round things. But the point is, the mask has to be modified in order to take into effect the optical things that happen due to the wavelength. It looks like we're in the process of going to extreme ultraviolet, which has a light source with 13.5 nanometer wavelength. Okay, so I need to mention the more modern process these days. There's still a lot of chips that are made using a planar process, but the high-speed digital chips, like in cell phones and laptops and servers, are now being made, and I think the FPGAs are being made using transistors that are FinFETs. And this is, instead of having a gate and then the source and drain below, these here, the gate wraps around the channel. Instead of being down below in the surface of the silicon, the channel is here underneath this gate. The source and drain kind of form this fin. Right? And this has better physical properties, right, as we will discuss later. As I mentioned early on, this was an idea that was invented here in this building, on this floor, I think. And so this is the so-called FinFET. That's the old planar device. And the newer devices are going to be with the gate wraps all the way around the channel, not just on three sides. So planar, the gate is on one side of the channel, and FinFET, the gate is three sides, and the newer devices will be, the gate will go all the way around, and these have even better electrical properties. That's probably coming up in the next process generation. Right? So real devices kind of look, look more like this. You can see these are the fins here, and these are the gate regions here. Right? So a lot of fins are put in parallel to make wider, stronger transistors. Okay, and I think I mentioned this the first week. So the state of the art these days for production is around 7 nanometer processes. That is again, it corresponds to the smallest resolvable feature size. 5 nanometer looks like it may be coming up. I don't know of any production devices yet. Right? And there's some experimentation with 3.5 nanometer. Okay, so that's all I'm going to talk about processing for now. I'm going to talk about transistor characteristics. Any more questions on the processing? Okay, so first thing about transistors that's important for this class is two things. It's the strength and the symmetry we talked about already. So symmetry, this is number 2 here. MOS transistors are symmetric. Source and drain are interchangeable, right? But usually they're designed to be used in one direction. Source is the node with the lowest voltage for an NFET or an NMOS transistor. In general, the source node is going to be connected to the power rail, which is for the NMOS transistor, it's ground, and for the complementary type transistor is going to be VDD, as we will see. The other thing to know is that transistors have strength, and the strength of the transistor is going to affect the speed of the circuit that it's used in. And the strength is proportional to the W over L in this picture. Now, in digital circuits, L is almost always going to be the minimum allowed, right? And the reason is, if we want strong transistors, we want to keep L as small as possible, right? And that will lead to this most strength for a given area, right? There's some design rules that says the minimum of L, what L can be. It's roughly 2 times the process resolution. So for a 7 nanometer process, it's going to be something like 14 nanometers here. All right? And pretty much all the transistors in the whole circuit will be of that length. But what we will do is use different widths. Designers will use different widths to get different strengths. Right? And by strength, it's the amount of current that it can provide for a given voltage, right? And that will affect the speed, as we see when we study the delays associated with CMOS circuits. So it's just something to keep in mind as we move through. And let me show you some transistors in action in a couple layout examples. And here the colors are similar to what I had used previously. This were kind of the standard colors, at least for some folks. Here's polysilicon is the blue. The red. The metal is in blue here, and the N diffusion is in green. And there's other type of diffusion, P diffusion, that we're going to use to make the complementary transistors, as we'll talk about later. This happens to be a NAND gate. NAND gate has 2 N-type transistors in series, which are shown here in the schematic. And here in the layout, there's 1 N-type transistor, here's another N-type transistor. These are relatively wide. You can see they're fairly wide. Okay, that's to make this gate operate quickly or have low delay, as we shall see. Here's some more. Here's another NAND gate layout. This one is a FinFET one. And you can see the FinFETs, instead of having these kind of continuously wide transistors, we have, if we want to increase the strength of it, we put more fins in parallel. Right? So here's a fin, 3 fins, actually running all the way through. And here's the polysilicon gate that you can imagine this kind of wraps around the fins, right? Which makes these 3 transistors, but these 3 transistors are all in parallel with one another, so they're all acting together. They're effectively acting like one wide transistor, as we'll see as we would see in a planar process. So these are the kind of layouts that would come as part of the standard cell library in ASIC design flow, and then would be used for generating the masks of the final layout. Okay, so I'm going to talk about transistor models a bit. So in this class, we're going to primarily model a transistor as a switch. You remember when I was talking about the operation a few minutes ago, we said if you put enough voltage on the gate, then it inverts the channel and the transistor turns on. It's kind of like turning on a switch. Right? It's not a perfect switch, though, in several regards. One is when it's on, there's actually some resistance in the channel, okay, which is a natural thing. It means it can't supply an infinite amount of current for a given voltage, right? Every kind of conductor that we can imagine in the real world has some resistance. Okay, so we'll think about what the on resistance, the so-called on resistance. It's the resistance of this transistor between the source and the drain when the transistor is turned on. The other thing that makes it not a perfect switch is that in order to turn it on, you need to get the voltage on the gate past some threshold voltage. Okay? So VGS has to be greater than VT. VT is the threshold voltage. Right? And for these transistors these days, it's like 1/4 of a volt. And if you have, even if you put some voltage on the gate, there's not enough voltage to get over to invert the channel, and so the transistor won't turn on. Right? So that's the other thing we need to keep in mind, is that there's a threshold voltage. Okay. But given that, besides that, we can model it fairly accurately as a switch with a resistor in series. Right? Now, I think it's useful to look below this abstraction to see how devices really work. Just not that we're going to use it much in this class, but just so you kind of understand the limitations of this abstraction. Right. So first, we'll look at the origins of VT, and we'll look at the on resistance of the channel, without going much into the physics, just looking at the kind of behavior of the transistors. So if we look at the way a transistor behaves, this is a measurement of this transistor in this picture here. We've got a voltage on the gate. The source is connected to ground. That's 0 volts. And then we're going to have some voltage on the drain. Let's assume that the voltage we put on the drain is I'm using 0.7 volts for VDD. It's VDD. It's the maximum voltage we have on the chip. Okay, so we have full voltage across this transistor. Right. And what happens then as we change the voltage on the gate is shown in this graph. So this is VGS. It's VG minus VS. VS is 0. So it's effectively just the gate voltage. As we increase the voltage, nothing happens. And what we're looking at is the current that flows. Right. So nothing happens, and all of a sudden current starts flowing. And it kind of gets, linear, kind of linear here as we get to higher and higher voltages, and we get to some maximum current for this transistor here. So the interesting thing to note here is that we've got this point here where this is an inflection point where it goes from not conducting much at all to conducting a lot, and that's the threshold voltage. And as I said, for these transistors measured here, it's about 1/4 of a volt. And then, so the transistor, we say, turns on when VG is greater than VT. We can look at what the current is when the transistor is fully on. For this measured one, it's about a milliamp, 1.2 milliamps. So this is the on current of the transistor. This is the maximum current when the transistor is on. And it's when it has maximum voltage across it, all right, VDD, and maximum current voltage on the gate. The gate's charged all the way up to high voltage. What happens down here is interesting too. Well, it kind of looks like I off is 0, but if you look carefully, it's not actually at 0. And so that's the other interesting thing about transistors, is they don't ever actually turn off completely. The I off is much smaller. It's going to be nanoamps than the on current, right? But it doesn't actually go all the way to 0 because we can't build we can't build a perfect switch. Okay, I'll say more about that in a few minutes. That's kind of explains the threshold part. So if you think about how the onness of the transistor goes with the gate voltage, it kind of turns on suddenly at this point. And that's because gets to a point when there's enough charge in the channel to invert the channel and turn the transistor on. The other thing I want to talk about is the idea of modeling a transistor as a resistor. And we like to do that. We really like this picture, as you'll see next week, and you'll be very happy that this is just a resistor, because if that's a resistor, then all the analysis of the timing of CMOS circuits gets very simple. We can do it all with first-order differential equations, just RC circuits, which you've studied RC circuits before in other classes. So we like to keep that as a resistor because then we have this kind of linear analysis. But it turns out transistors are not really resistors, they kind of look like this. This is showing, for this device, the current as a function of the voltage across the source to drain. Right? Now, and each curve here is for different amounts of gate voltage. And I said it's nonlinear. It's nonlinear in this very interesting way. It saturates. If we get the gate voltage, the VDS, drain to source voltage, pass some relatively small amount, then the current becomes independent of the voltage across it. It looks more like a current source. Right? It's got this saturating nonlinearity. Right? When we say it's a resistor, when we make that approximation, we're saying that this one of these curves, pick whichever one, let's say take the top one, we're saying that curve is not shaped like that, it's shaped like a straight line, right? Because a resistor on this plot would be a straight line. It would be that the current is directly proportional, linear proportional to the voltage, but it's not. So just something to keep in mind later when we're looking at the timing characteristic of circuits, we're going to assume that they behave like a resistor with the appropriate value of resistance to kind of approximate this curve, the top curve usually. So we do this linearization because it makes all the delay and power calculations simple. All right. Usually it just turns them into first order differential equations, R's and C's, and the solutions to those are just exponentials. So if we look at the waveforms associated with signals that are changing inside our CMOS circuit, they're going to look like exponentials, but actually they're not quite exponential because of the fact that the transistors are not quite linear. But for all intents and purposes, it's close enough. If you really, really care and you want to simulate a real device without building it, you can use something like SPICE. And SPICE is a circuit simulator that models transistors this way. It actually has either an empirical model or a numerical model, empirical or analytical model that captures this nonlinearity. Right? And people who do analog circuits, of course, they care about that. And so they will model it that way. Us doing digital circuits, we don't really care that much. We can get a pretty good approximation by modeling things as resistors. Okay, so I just wanted to show you that so you know that this is all kind of not totally accurate, but it's accurate enough. Okay, so here we are with our MOS transistor here. We've got this model. If the gate voltage is too small below the threshold, then it's an open circuit. And then if the gate voltage is high enough, the transistor looks like a resistor with some equivalent resistance. Well, this is not quite right either because this part is wrong. When the gate voltage is below threshold, the current through the device, the resistance doesn't go to infinity. The resistance gets very big, but it doesn't get infinite. Right? And we can see that if we take this plot I had earlier, we looked at this, which was the current through the device as a function of the gate voltage. And it's hard to see what's down here, but if we plot this on a log plot, then we can see it better. And a log plot will expand things out for us. So that's the log plot version of that one. And what we can see is there's a y-intercept here. When the gate voltage goes to 0, there's still some residual current that is through this measured or simulated device. Right? And before we had that exponential, very flat exponential, that's a straight line here. And when we had that linear looking thing, it kind of looks like that. Here's the threshold voltage here at this point. Now, there's our on current. And here's, now we can see the off current. And in this device, measured device, it's about 10 nanoamps. So it's orders of magnitude, that milliamps up here, right? And so they differ by, what, 6 orders of magnitude or something like that, right? So There's a tiny amount of current relative to the on current. Our on currents are relatively big compared to the off currents. But this will become significant as we see later when we study power dissipation in CMOS circuits. If you have all these transistors that you think are off and they're all leaking, effectively you're going to make a short circuit between VDD and ground, and this is power that's being wasted, just even when the chip's doing nothing. If you have a billion transistors, even though you have nanoamps here, you end up with a significant amount of current that's just lost to the fact that the transistors are leaky. Okay? It's like leaky pipes. We're wasting. All right. So interesting thing about this curve, the shape of the curve is kind of fixed. It comes with the territory, the physics of the transistors. Right? The process engineers can move this curve left or right. So the process engineers can increase I on, which is good. As we will see, the more current we have in a given situation, the faster the circuit will be. Right? But if we can do that by raising the moving the curve to the right. That will raise I on, so we get more current for a given transistor. But oh, sorry, this way. If we move it this way, push it left, I on will go up, but I off will also go up. Right? So you can make faster transistors, but it comes at the expense of having more leaky transistors. So you leak more power that way. You can decrease I off, but it lowers I on. So we can decrease the leakage, but it slows down it decreases the on current and thus slows down the circuits. So we'll see this. This is a constant kind of trade-off for process engineers figuring out the right ratio between I on and I off. Okay, so back to one thing. Now back to FinFETs. The one thing that FinFETs did is they changed, because of the shape of the transistor, it changes the electrostatics, and it changes this property of the curve so that the so-called subthreshold slope, which is the slope of this curve measured on a log plot. This was the planar device that I just showed you a minute ago. It has off current here. The Tri-Gate, or the FinFET device, has a steeper subthreshold curve here, and it intersects closer to 0, so it has less leakage. So that's one of the reasons why FinFETs are so popular, is that for a given on current, it has less off current. So it lowers the power consumption associated with leakage. So the trade-off that we had before, as I mentioned, is a little easier to make. Okay, so let's see, where are we? All right. So here's a more realistic switch. So this is a better model then. We have the on resistance for when VGS is greater than VT. And we have the off resistance when VGS is less than VT. So when the transistor is supposed to be off, has low voltage on the gate, it has very big resistance here, and it has a small resistance here when it's on. Right? And like I said, these are like 6 orders of magnitude different. Okay, so that's kind of, and now we're going to move it up into a logic perspective. How do we think of this as a logic device, or a device for building logic circuits? Right? And well, one place we can start is we can say, think of this in terms of these Boolean variables here, x, y, and z. We can say if x is equal to 1, then y is equal to z. Right? It's kind of the logic associated with closing the switch. So forget about the currents for a minute. We just think about making connections. So if x is a 1, the switch is closed. We have connection between source and drain, so x gets equal to y. I mean, y equals z. Right? Turns out p-type transistors, which I didn't talk about much, but they work in the opposite way. They work in this way, logically. If y equals z if x equals 0. So p-type transistor, you can kind of think of like an NMOS, N-type transistor, except instead of putting a high voltage on the gate to turn it on, you put a low voltage on the gate to turn it on, to close the switch. All right. So it kind of looks like this. So it's actually has a negative threshold voltage. So if the VGS gets negative enough, more negative than the negative threshold voltage, then it will turn the device on. Okay, so we can use these two devices, N transistor and P transistor, to make first an inverter, our first kind of CMOS logic circuit. We use a NFET or NMOS transistor here and a PMOS transistor here, connected in this configuration. The gates are connected together. The drains are connected together. And the sources are the source of the NFET connects to ground, and the source of the PFET connects to VDD. So since in the PFET, the current flowing is not electrons, it's holes, so the current through a PFET actually flows from its source to its drain. The current through an NFET flows from its drain to its source, because that's electron flow, and electron flow direction is opposite. The current is opposite of the flow of electrons. Okay, this showed a picture of a capacitor here. We'll talk a lot more about this capacitance later. For now, just imagine this is a model of all the capacitance of whatever this inverter connects to. Right? There's some internal capacitance here. There's some capacitance on the wire. There's capacitance for the inputs to other gates that this might connect to. Right now, just think of it as CL. And we won't talk about the capacitance much until next week. Okay, so how does this thing work as an inverter? It's kind of like this. If the input to the inverter is high voltage, what's going to happen is it will close the switch here at the bottom. The end device will be turned on, which connects the output down to ground through resistance. And the pull-up will be effectively open, very high resistance. Right? So that means the output, then it will get turned to a 0, because this is the source of 0, is the ground. If we put, so that means a 1 at the input, 0 at the output. If we put a 0 at the input, this NFET is open circuit. The PFET switches on, connect the output to VDD. So 0 at the input, VDD at the output. That means 0, logic 0 at the input, logic 1 at the output. So acts like an inverter, just the way we want. Okay? So we can extend this now. And this is, for now, first order analysis, meaning we're ignoring the capacitance. Next week, we'll talk about the effect of the capacitance, which slows down the switching. Right? And that's why there's delay. But for now, we're just thinking about the functionality, the logical functionality. So how can we build logic out of this? Well, we can kind of generalize this idea with the inverter to make other types of logic gates. You've probably seen these before. But the idea is this. At every point in time, and this is so-called static CMOS logic, at every point in time, except during the switching transients, each gate output is connected to either VDD or ground via a low resistance path. So we know that here. If we put a 0 here, this P-type transistor is turned on, and there's a low resistance between VDD and the output. And otherwise, we have a low resistance here. But for whatever input we put here, there's a low resistance path to the between the output and either VDD or ground. Right? So we can put switches in series or parallel to build more interesting circuits, obviously. So in series, it's kind of logically like this. If we get an AND, right? So X equals Y if A and B are both true or both are 1, right? Because both the switches have to be closed. And in parallel, we kind of get the OR. If one or the other is true, then we get X equals Y, right? in this kind of switch type logic here, this isn't useful by itself. I mean, you could try to build logic circuits this way. The problem is the output's undefined if the condition's not met. So if X and B is not true for some reason, then this output here is undefined. It's not connected to anything, right? So we need to provide a contingency for the other cases. So that's what we do in CMOS is we cover all cases, right? Just before I do that, though, I can look at the inverting switches, the PMOS transistors. They kind of give us this. They say X will connect to Y if A bar and B bar, right? Which we can use De Morgan's rule and say this is the same as A or B not. Okay? Likewise, we get kind of an AND operation when we put P-type transistors in parallel. We'll say that X equals Y if A bar or B bar, which is the same as A and B bar. Right, so this is the principle then we use for all these simple CMOS logic gates. The NAND gate is an example of that. All right. So to remind you of the truth table for NAND, here's the enumeration here. We have 4 possibilities. The output is a 0 if and only if A and B are both 1s. Right. So we achieve that here. We want the output to be a 0 if both A and B are 1. Therefore, we're going to put 2 NFETs in series here. If A and B are both a 1, then both of these switches will be closed and the output will connect to ground. So the output will be 0 in that case. In every other case, one of the pull-ups or both will be switched on, and therefore the output will be a 1. Okay, so logically, it's pretty simple to understand how this thing works. You can think about it this way also, is that there's 2 functions here. The pull-down network, which I called PDN here, the pull-down network, and there's a pull-up network. The pull-down network has this function AB, and that says if this function is true, then we have a conductive path from the output to ground. Right. So we generate a 0 if this function is true. Right. And then pull-up network is this. It's a, since the symbol reminds you that for P-type transistors, it's effectively inverting the signal that connects to its gate. So this is A bar or B bar, which through De Morgan's theorem says A times B bar. So this gives us a conduction to VDD under this condition, which means either A is a 1 or B is a 1 or both. Right? No. A is a 0 or B is a 0 or both. Yeah. So that's all this part of the truth table. Right? And that's where this pull-up is active. We will see in our CMOS circuits, CMOS gates like this, we use P-type transistors for pull-ups and N-type transistors for pull-downs, and we don't mix those. And I'll talk later about why that is. But for now, you can make that observation. So we can generalize this idea of implementing a logic function in a single gate by kind of this. This is a generic static CMOS gate. There's a pull-down network. There's a pull-up network. And inputs go to both places. Right? All the inputs go to both places, pull-up and pull-down. As I said, the pull-down network is some connection of N-type transistors, and the pull-up network is some connection of P-type transistors. To make this work right, the pull-up and the pull-downs are dual logic networks. Right. So what this means is series connections in the pull-down are parallel connections in the pull-up, and parallel connections in the pull-down are series connections in the pull-up. Right. We saw that here in this gate. Here we have two transistors that use A and B in series for the pull down. Those transistors are in parallel to simulate the p-type version of that, the pull up. The transistors for A and B are in parallel in the pull up. Right? That's an example of a dual, but they can be more complicated. That's a very simple dual. Right? The other thing is that the pull up and the pull down functions are complements of one another. Right? The functions associated with the switches are complements of one another. What this means is that it guarantees that they're mutually exclusive, and under all input values, one or the other is conductive, but never both. Right? Think of what a complement is. In terms of a truth table, a complement function, if you have a function that has some ones and zeros, the complement function will have a 1 everywhere where the first function had a 0, and vice versa. So they cover all cases. The fact that they're complements means for any input combination, either the pull-up network or the pull-down network will be on, but they'll never both be on. If they were both on, then we have a short circuit between VDD and ground, and that would be really bad. If there was some case where not one or the other were on, where they're both off, that would be bad because the output would be undetermined. Right? So we want to, under all circumstances, have this output be connected to either VDD or ground through a low resistance path. And that's guaranteed by making sure that these functions are complements of one another. And that comes from the fact that they're dual logical networks. So it's a very simple idea, but it's kind of a powerful idea. Here's another example. In this case, it's the NOR gate. So we want the output to be a 0 if either A or B is a 1. Right? So we get that by putting these in parallel. We get this kind of OR pull-down operation. Right? And the dual of that then is just put the transistors in series. And that covers all the other cases. So you really only need to think about, with CMOS gates, you only have to think about one half, the pull down or the pull up, and the other one is just kind of comes as the dual. Right? So it makes it really easy that way. And if you keep it as a dual, then it will take care of all the properties that we need. Now, here's a complex, more complex function that we can also implement as a single CMOS logic gate. Here's the function here, D or A, and with B or C. Right? So this is kind of easy to construct in this case because this is a kind of a prescription for how to make the pull down, because we want the output to be a 0 if the function that's under the expression that's under the hat, under the bar, is true. Okay, how do we make that be true? Well, we configure the transistors like this. So we've got D or A ANDed with B or C. So the BC OR part are these B and C in parallel. The ANDing of that with A is putting A in series with those. And then ORing in the D is putting D in parallel with everything else. And if that function underneath the bar is true, then the output's connected to ground. That's basically what that complement means there. It means the function generates a 0 in that case. Right? And then, by our principle of the dual, we can figure out what the dual network is. So here, D is in parallel with this stuff. So up here, D is going to be in series with this stuff. Okay, to make this stuff, we have A in series with B and C in parallel here. A is in parallel, B and C in series. So we just switched all the series connections to parallel connections, and we get the dual. Anybody see how that works? So you should be able to then take any logic function and figure out how to make it in a single CMOS logic gate. Now, for various reasons, this idea we won't extend this to very large functions, because if you start piling up a lot of transistors in here, everything gets very slow. Right? At that point, we're better off breaking it into smaller gates and putting connecting gates to one another through normal means. But this principle could be used for making larger and larger logic gates. So here, here's another one. I'll just show you this one on the board. So we have D. We got a OR here. So we have a parallel connection of two series subcircuits. So we've got D. Oops, that doesn't work. So we've got A and D, and then that's in parallel with B and C. That's B and C. So that's the output. And then the pull-up, make the dual of that is, so those two which are in series here are going to be in parallel, and those two which are in series are going to be in parallel. And then those two branches that are in parallel are going to be in series. So we'll end up with these are P-type. It's VDD up here, and then that's AD, and this is B and C. And this is the same as out. Okay. And, you know, if you don't trust it, you can just try all the input combinations and prove to yourself that it is the correct function. Okay, I'll show you one more thing about making duals. So most of the time, it's very simple to figure out the dual, like I was just doing here. You figure out you look at what's in series in one network and then put them in parallel in the other network and vice versa. There's a graphical way that you can use for doing this as well, which I've shown in this slide. If you look at this pull-down network here, which is kind of similar to what I had a minute ago, you can use a graphical method where here in the solid line, we put a node for each connection. So there's electrical node here, and one here, and one here, and one here. So we got those 4 nodes. And these are these circles here. And this one's connecting to the output, and that connects down to ground. And we got these intermediate ones. And then the arcs, we use arcs to connect the nodes together, which are representing these transistors. These connections between the nodes is where the transistors are. And so we label these arcs with the variable name that is the input to that transistor. Right? So here, A and B transistors are in parallel with one another. So you have a node in between, the I1 node, and then the B arc is labeled here. The C arc is labeled there. There's I2, and then the D arc is labeled there. Okay, so you do that for the pull down. And then you go 90 degrees to that. You can put a node for VDD for the pull up. You put a node over here for the output. And then you put a node in any of the regions that's enclosed. In this case, put a node here. We've got this region covered by that node. This region is covered by that node. And this region is covered, this region in here of the graph is covered by that node. And then you connect these nodes together. And when you cross an arc, when you cross an arc from the original graph, that arc takes on the variable of that arc that it crossed. So this arc here is going to be A, that arc's going to be B, that's going to be D, and that's going to be C. So this new graph here shows us that we need to put D and C in parallel with one another, B and A in parallel with one another, and then those two parallel connections are in series with one another. You rarely will need to do this, but I think I'm going to give you a homework problem where it's only solvable using this way. People see that then? So you can do this for any of these networks. Remember, you turn 90 degrees and you put a node. You have to cover all the regions. This outer region is divided by the output and ground. So you got a region here, and then in this case, just one region in the middle. Okay, how much time? 4 minutes. Okay, I'm just going to touch on this, and I'll probably repeat it next time because it's important, but you should see this. Okay, non-inverting logic. So everything I've shown you so far is inverting logic. Like, I didn't show you AND gate or gate. You know, if you're trying to build an AND gate, for instance, you could say, well, why not do this? Use N-type transistors here, the pull-up. So that would say the output would be a 1 if A and B are both a 1. That would be a logical AND, right? And then down here, we could put the P's to handle the other case. Right, so if A and B are both 0, well, let's see. Okay, if this were to work, then out would be a 1 here. And then in every other case, one of these things would be on. They'd be a 0 here, so you get zeros here. And that would look like an AND. We don't build gates this way because NFETs don't make very good pull-ups, and PFETs don't make very good pull-downs. Right? And the reason is, it goes back to this threshold voltage that I was talking about a minute ago. So in this configuration, we have a P-type transistor here connecting to some node connected up to VDD. Right? If we put a low voltage on the gate here, this transistor turns on, and this node will get pulled up to VDD. There's some capacitance here, so it takes a little bit of time to discharge the capacitor. Likewise here, for pulling down, we put high voltage here. We have VGS of a big voltage is way past the threshold. The transistor will turn on, and this output voltage will eventually go down to 0 because that node gets connected to ground. If we try to do it the other way, if we try to use a P-type, N-type transistor to pull up this node here, what's going to happen is if this node were at 0, we turn on the transistor by putting a high voltage here. What happens is, as this voltage goes higher and higher, we'll get to a point where VGS, which is here, is going to be VT. And then the transistor effectively turns off. It hits its threshold voltage. So you can't get this point higher than VDD minus VT. Right? Once this gets to VDD minus VT, then VGS is equal to VT, and the transistor effectively turns off. Right? It's because the built-in threshold. Likewise, pulling down with it. So this configuration with N-type doesn't make a good 1. This 1 is degraded by 1 VT, which for us is like a 1/4 volt out of 0.7 volts. Same thing going this way. So you could do it for one stage. You get a weak, this output would not be all the way to VDD, or it wouldn't be all the way to ground, right? But then if you put that into another logic gate, it would get worse, and these effects kind of accumulate, and you get to the point where you can't distinguish the 1s from 0s anymore. And if you look back at my curves, it's actually worse than this. It actually slows down. As the voltage gets higher and higher, it turns the device off. It's moving down those curves, and it gets slower and slower and slower. So not only does it end up at not a very good logic value, it takes a long time to get there. So our rule is, it's kind of tough luck. I mean, that's what comes with the territory. And so we don't build non-inverting gates, which means we have inverting switches, p-type on the pull-up and n-type on the pull-down. And so if you need a function like this, like AND, right, the way we build it is NAND followed by invert. Right. And that's probably the best way to do it. Or get rid of or do it all with NANDs and somehow push the bubbles around, and it'll kind of work out. A few inversions here and there don't really matter. Okay. All right, so here's kind of a summary of this then, and then we're done for today. So we're going to use n-type pull-downs, p-type pull-ups. This gives us full rail-to-rail swings. When the input to a logic gate is stable, that means once the inputs change, the output will be stably connected to VDD or ground. So there's no power. Besides the leakage, there's no current flowing once we do the switch. Right? There is, as we will see when we switch, when change the inputs to a logic gate, like the inverter goes from 0 to 1, there's instantaneously, during that switching time, a time when both the N and the P-type transistors are on. And there's a little burst of current that shoots between VDD and ground there. But once it stabilizes, there's no static power consumption except for the leakage, right? Which also allows us to build very big circuits because they don't consume much power. They really don't consume power when they're switching. Right? So that's it for now. I'll see you on Thursday. We'll continue with some more CMOS circuits.